Hey, there you are. Okay, that's my people. So, today is the second day of Calc 2. You guys ready? We're going to talk a little bit about limits. I'll remind you, because I know not everybody's always able to make the first meeting, I'll remind you the very, very basics of what we talked about last time. But then today we are going to get into some of the nitty-gritty. So make sure you're taking careful notes. I will get things switched over to my document camera, and we can get started. Yeah. So this is section 4 of MAC 2311, and this is a lecture, and today is the 26th. Today, we'll review the idea of secants and tangents, but then we're going to start talking about limits of functions. And we'll learn some special notation. Okay. So the way we're going to approach the concept of limits is through graphs. We're going to look at graphs of functions first, and we'll talk about how to find limits based on the picture, the graph of the function. And then the next lesson, we're going to talk about some algebraic methods for finding limits. But for now, we're going to stay focused on the graph thing. Before we get into that, though, I want to talk to you a little bit about secants and tangents, just to remind you kind of what we've been doing, where we're going. I also wanted to let you know that the office hours, I have updated. I will have an office hour today. If you go to our class in Canvas, you'll see now that the office hours portion, instead of saying to be announced, says Monday, Wednesday, 3:30 to 4:30, and you can click this link during those times to join that Zoom meeting. And then Tuesday, Thursday, 12 to 1, click this link to join that meeting during those times. And then I'll be adding a couple more. But those are the ones that I've nailed down for sure. And that's how you join. So if you wanted to come to the Wednesday office hour today at 3:30, you would come here, click this link, and it'll get you into that Zoom meeting. All right. So recall a secant line is a line that joins 2 points on the graph of a function. And so what we're going to do, how do I want to draw this? Let's draw it like this. What we're going to want to do is think about keeping one of these guys fixed and slowly walking the other one over towards him. So this line, this dotted line that I've just drawn in, would be the secant line to this function from A to B. The slope of that secant line, remember, is the average rate of change for that function from A to B. And what we're going to want to do is slowly start thinking about how to bring this point B closer and closer to this point A. So this right here is a secant line. And it does represent a rate of change. Like if f of x was measuring how much water there is in a tub as it fills or drains, then the slope of this line would tell you how many gallons per minute have drained out over the time from A to B. So it's a rate of change or a speed. The reason we're going to start talking about limits or one of the main reasons we're going to start talking about limits today, is because we want a process that will allow us to go from this secant line, or the slope of that secant line, to this tangent line. So this is the tangent line. So the slope of the secant, that's the average rate of change. So you can think about maybe if your function is measuring position and your horizontal axis is measuring time, then this average rate of change would be your average speed from time A to time B. The tangent line gives you your instantaneous rate of change. So you can think about the slope of the secant as being like how fast you were going overall on that trip. What was your average speed? Sometimes you're going fast, sometimes you're going slow. And you can think of the tangent line's slope as telling you how fast you're going at any given moment. So like, what is your speedometer reading right at that moment? The challenge here is that this average rate of change, this is f of b minus f of a, the y2 minus y1 over b minus a, x2 minus x1. If you plug in b, if you send b to a, if you plug in a for b in this formula, if you try to plug in the same number for a and b, then the bottom is 0, and the top is also 0. So evaluating this expression where you send b closer and closer and closer to a becomes challenging. And that's why we need the tool of a limit. That's why we have the mechanism of limits. It's to allow us to interpret what happens as those numbers get closer and closer together. So we're going to deviate from talking about secants and tangents for a little bit. And I'm just going to talk about limits, how to find limits. And then we're going to come back to the whole secant tangent picture to introduce the concept of the derivative. It turns out the slope of the tangent line, this is going to be the derivative of the original function, whatever that means. You may have heard the word before. So let's talk about limits. Let's see, did we want to do a concrete example, something like that? Let me remind myself what I put in your homework recently. I don't think I gave you anything brutal there. No, yeah, this is all really clear. Okay, yeah, we're ready to talk about limits. Okay, so this is the start of chapter 2 officially. Section 2.1 on limits. The idea of a limit is that you want to ask not what is the y value on the graph of a function at a particular point, but what y values do you get if you start sneaking up on that point? So let me call this C, and suppose I have a graph that looks something like this. Maybe like this. There's a hole in the graph here. And let me just call that value, the y value of that hole, L. If this is the graph, y equals f of x, notice that due to the hole, f of c is undefined. right? If I look along this graph right above C, there's a hole there, it's not filled in. So I can't say what f of C itself is. But if you imagine a little dude walking along this graph, getting closer and closer and closer to that x coordinate, you can ask yourself, what would his y value be getting closer and closer and closer to? So even though f of C is undefined, we say that the limit, and I'll write it out in English here first, the limit as x approaches C of f of x is L, because if x gets closer and closer to C, then f of x gets closer and closer to L. This is the intuitive definition of a limit. So we say the limit as x approaches C of f of x is equal to L means the same thing as saying, well, if you let x get closer and closer to C, then f of x, the y values, will get closer and closer to L. The notation for this, we say lim x approaches C of f of x equals L, like that. And we can define this rigorously. Outside of the intuition land, we want to get comfortable coming up with definitions that aren't subject to interpretation. So like, what does it mean to say get closer and closer to? That's kind of subject to interpretation. That depends on what the words mean to you. So we want to come up with a definition that is unambiguous. The strict definition, we say the limit, so lim x to C of f of x equals L, provided, for us, we think of this in terms of a one-sided thing. Provided the limit as x approaches C from the left, and I'll explain the notation, equals L, and the limit as x approaches C from the right of f of x equals L, where the two limits lim x to C minus f of x and lim x to C plus f of x are called one-sided limits. There is a way to do this that is entirely unambiguous using deltas and epsilons, but usually if I drop that right away, people kind of get frightened. So the way the textbook prefers to do it, and the way most calculus classes at the university level do it, the first calculus class is like this. They define these two one-sided limits, and then they say that the overall limit, this guy, is equal to L, as long as both of the one-sided limits are equal to L. And these are relatively easy to understand intuitively. So let's look at some one-sided limits. Maybe I have something like this here. No, something like this up here. So here's my function f of x. Here's C. And I'll call this guy the height here y1, and I'll call this guy the height here y2. So the hole right here is at height y2, and the filled in spot right here is at y1. If I'm walking a little guy, imagine a tiny little guy or a little ant or something, walking along this graph, getting closer and closer to having x coordinate c, but coming in from the left. Then his y value will be getting closer and closer and closer to y1. So here, the limit as x approaches c with the minus here, meaning from the left of f of x, that would be equal to y1. On the other hand, if I was walking along this graph and I wanted my x coordinate to get closer and closer to c from the right, then my y values would be getting closer and closer and closer to this guy, which is up here at y2. So this is a case where the left and right limits are not equal. And if we come back to our definition, what it means for the limit as x approaching c to equal some number L, that would mean that the left and right limits have to both be equal to that same number. So since the limit as x approaches c from the left of f of x is not equal to the limit as x approaches c from the right of f of x, we say that the overall limit as x approaches c without any plus or minus does not exist. So this is the fundamental concept behind limits from the Calc 1 perspective. You imagine walking along your graph and trying to sneak up on the point in question. So here the point in question, or the x value in question, is c. I want to know, what is my function f of x doing nearby c? If I try to sneak up on that point from the left, if I walk along the graph, getting closer and closer to that point from the left, my y value is getting closer and closer to this y value, y1. However, if I was sneaking up on that point from the right, if I was walking along this graph, getting closer and closer to having x coordinate c from the right, then my y value is getting closer and closer to this guy. And since these are not the same, the left limit and the right limit are not equal. Okay, so the overall limit does not exist because the left limit and right limit are not both equal to the same thing. I think some concrete examples will help make this a little bit more clear. But for now, do you guys feel comfy or have any questions about what it is we mean to talk about the left limit and the right limit? Do you have an idea for what I mean by sneaking up on this point, walking along the graph? So as this guy walks left and right, his y values go up and down. We think of us as having control over the x value, and we watch what happens to the y values. So I try to send the x value closer and closer to this point. If I do it from the left, then the height this guy is at will get closer and closer to the height of that point. But the height of this guy coming in from the right is closer and closer to the height of this hole, which is not the same as that point.
So y is like the first one negative and like c negative and then c like plus.
I couldn't hear the start of that. I'm sorry. Could you say it just one more time?
Y is it like c negative and then c plus?
So this negative means from the left. And this plus means from the right. That's the idea. So as I come in towards C from the left, that's this side. So I'm getting closer and closer to the height y1. But if I came in from the right, that's looking at this side, then my heights are getting closer and closer to y2. Make sense? All right, let's find some concrete examples we can look at. Come here. Yeah, let's look at something a little bit tricky. That's good. So, let's look at or look for the limit as x approaches 1 of f of x, where f of x is x squared minus 1 over x minus 1. I don't have a graph yet, so I'm going to have to start by drawing a graph. When asked to calculate a limit, the first thing we should try to do is just plug in that x value. So if we're lucky, we can just plug in x equals 1. Let's see, so the limit as x approaches 1 of x squared minus 1 over x minus 1. Maybe we'll get lucky. Let's see, is that 1 squared minus 1 over 1 minus 1? No, there's a problem, right? 1 squared is 1, so 1 minus 1, the top there is 0, and 1 minus 1, the bottom there is also 0. This is trouble. We can't divide by 0. So I can't get this just by plugging in. However, f of x is x squared minus 1 over x minus 1. Let's see if we can't make this a little easier to work with, get somewhere we can have a picture. If I factor the top as a difference of squares, x squared minus 1, that's the same as x minus 1 times x plus 1. And then downstairs here, I also have x minus 1. So this factor can cancel. This is equal to x plus 1 as long as x minus 1 is not 0, i.e. x is not equal to 1. So for all x values besides 1, f of x is equal to this linear function x plus 1. And at x equals 1, it has a hole coming from that canceled factor. So let's draw the graph. All right, well, here's y equals x plus 1. We'll have a hole here. So this is the graph y equals f of x. This is 1. This is x. So remember what I'm trying to do. I'm trying to find the limit as x approaches 1. So we should look at the limit as x approaches 1 from the left of f of x. and the limit as x approaches 1 from the right of f of x. We want to check these two one-sided limits. If these two one-sided limits are equal to each other, then that shared value is the value of the limit overall. So if I'm a little guy walking along this graph, getting closer and closer to the x coordinate 1, is my y coordinate getting closer and closer to anything in particular?
2?
Yeah, the y value of this hole, which is 2. We know that the y value of that hole is 2 because this function is x plus 1 everywhere except at 1. And the y value of x plus 1 when you plug in x equals 1 is 2. So the left limit, the limit as x approaches 1 from the left of f of x appears to be 2. What about the right limit? What if I'm over here? If I'm coming in along the graph this way and I let my x coordinate drift closer and closer and closer to 1, my y value is also getting closer and closer and closer to 2. So the limit as x approaches 1 from the right with this plus of f of x is also 2. Since both one-sided limits are equal to 2, the overall limit lim x to 1 f of x does exist, and that shared value, the value that these two one-sided limits have, that is the value of the overall limit. And lim x approaches 1 f of x is equal to 2. So the skill that I would like you guys to be developing today and tomorrow as you work on the homework is taking a look at a graph and being able to see the one-sided limits at any given point. It's not terribly hard, but it does take a little bit of getting used to. I can do some problems from your homework, but maybe let's see, is there anything super interesting in here? Heaviside function is fun. Yeah, okay, so this is what we just said, that the overall limit as x approaches a of f of x is equal to L if and only if the two one-sided limits are both equal to that same value. So let's start with the Heaviside function, and then we'll look at a couple other little piecewise examples, and then I'll do a few problems from your homework. So let's find, if possible, the limit as x approaches 1 of h of x, the limit as x approaches 0 of h of x, and the limit as x approaches -1 of h of x, where h of x is this piecewise function called the Heaviside function. It's 0 if, sorry, let me come back here. 0 if x is less than 0, and it's 1 if x is greater than or equal to 0. So I'll give you guys a second to write this down, and then I'm going to draw the graph of this function, and we'll see if from the graph of this function we can figure out the value of these three limits. So we want to find, if possible, these three limits. The limit as x approaches 1 of h of x, the limit as x approaches 0 of h of x, and the limit as x approaches -1 of h of x, where h of x is this piecewise function. H of x is equal to 0 if x is less than 0, and it's equal to 1 if x is greater than or equal to 0. This is called the unit impulse function. It's important in certain kinds of signal processing and differential equations. So we need the graph. The graph is all we have to go on right now. Our understanding of limits is just based on graphs. All right. So this piecewise function, it's 0 if x is less than 0. So it's down here. For all x is less than 0. And then it's equal to 1 if x is greater than or equal to 0. So you've got a filled in point here, and then it's constant function y equals 1 everywhere to the right. And this guy down here, he's open. So the y value, or the x value 1, I'll put right here. The x value -1, I'll put right here. And I know it's a little bit hard to see, but the graph is sitting on the x-axis over on this side. So hopefully everybody can recognize that graph. Okay. So we've got 3 limits we want to sort out, which means we've got 6 limits that we need to think about overall. We need to think about the left and right limit for each of these guys. So let's look first the limit as x approaches +1 from the left of h of x. So here's the point at x equals 1. If I'm a little guy on the graph walking closer and closer to this point from the left, is my y value getting closer and closer to any particular number?
No.
Let's imagine. So here's my little guy. He's walking closer and closer to this point. What's his y value right here?
1.
And right here?
1.
Also 1.
And right here?
1.
Right here? All right, so as we get closer and closer and closer, his y value is always staying 1. So the limit as x approaches 1 from the left is 1. What if I'm coming in from this way? Well, right here, my y value is 1. 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 As I get closer and closer to this point, my y value is staying 1 there also. So the limit as x approaches 1 from the left and from the right of h of x is 1. So because these guys are equal, the overall limit does exist, and the limit as x approaches 1 of h of x is 1. Let's look at 0 next. 0 is a little bit interesting. You'll start seeing that there's connections between the idea of continuity and this idea of limits. Imagine I'm a little guy on the graph just to the left of 0. That means I'm over here. If I start walking towards x equals 0, like this, what are my y values getting closer and closer to?
0.
Yeah, they're always 0, right? Right here it's 0, right here it's 0, right here it's 0. What about the limit as x approaches 0 from the right? So that would put me up here, walking that way. What are my y values getting closer and closer and closer to there?
1.
1, yeah, they're always 1 up there. So the limit as x approaches 0 of h of x does not exist. Because the left and right limits aren't equal to one another. Remember, we say that the overall limit exists if those two one-sided limits are equal to each other, and then that shared value is the value of the overall limit. If those two one-sided limits are not equal to each other, then we say the overall limit does not exist. And it's because there's this sudden jump here. If I try to sneak up on 0 from the left, I end up staying down here. If I try to sneak up on 0 from the right, I'm always up here. There's not a smooth transition. There's not a nice connected graph there. There's this jump, and there's a meaningful relationship between these limits not being equal and the function being discontinuous there. All right, what about the limit at -1? Let's try to do this without drawing any little dudes. So if I want to look at the limit as x approaches -1 from the left, I would write lim x to -1 and then the little negative up there. What is this? If I'm over here sneaking up on -1 from the left, what are my y values getting closer to?
0.
Yeah. And the limit as x approaches -1 from the right of h of x? If I'm over here sneaking up, yeah, 0. So the overall limit as x approaches -1 of h of x, that does exist, that's 0. And there's nothing sacred about 1 or -1. I could have chosen any negative number and the limit there would have been 0. I could have chosen any positive number and the limit there would be 1. The interesting thing happens here at 0 where you have this discontinuity. Okay, let's take a look at one more little example from the book here. And then, no, this is good, okay. So we're gonna look at this guy, example 7. And I'll copy that picture down here to the best of my ability. You should do the same. Okay, this is here. And then we do a little thing like that. Here, right there. Okay. That's open, we'll fill it in down 1. And then it continues off like this. Okay. So I'll call this function g of x. Each tick mark here is 1, so this is 1, 2, 3. 1, 2, 3, 4, 5. This guy right here is open. And then you've got a filled in point down here below. If I'm walking along the graph and I try to sneak up on x equals 2 from the left, so I'm on the graph of g, and I want to have x approach 2 from the left, I'm asking where is this guy's y coordinate going as he walks along that graph, getting closer and closer to that hole from the left. So what is that value?
3.
Mm-hmm. And what if I wanted to sneak up on 2 from the right? I want to look at x approaching 2 plus of g of x. Well, that would mean my little dude is down here because he's stuck to the graph, but he's still trying to walk up towards x equals 2. So what's he getting closer and closer to?
1.
He's getting closer and closer to 1, yeah. So does the limit as x approaches, what can we say about the limit as x approaches 2 of g of x?
Doesn't exist.
Good. And that's because I cannot say overall, as x gets closer and closer and closer to 2, that g of x gets closer
I have a
to
question.
any particular value.
Hold on. I have a question. So while I was doing the homework on question 7, there was an example just like that. And one of the problem, if like the answer was like doesn't exist, but I said like does not or not defined as like another way of saying it while I was reading through the book. And for some reason it wasn't taking it. I don't know why. Or do I have
Yeah,
to?
for undefined, you have to type in DNE.
If you're, yeah, in WebAssign, so if the limit does not exist, they want you to type the letters D, N, E. But I'm not sure that what you're talking about is the same thing that we're talking about here. So I made a note, number 7 will be the first example I do from the homework, and we can take a look.
Yeah, that's the one.
All right, let's do that. We'll do that next. But before that, I want to do a couple other things here.
Okay.
We're talking about what's going on near 2. Can anybody tell me what is G of 2?
1.
Good, it's 1 because this is the guy that's filled in, right? So remember the y value that's actually on the graph at x equals 2 here is 1. So anytime you're analyzing a function at a particular x value, there's 3 things I'd like you to be thinking about right now. The limit from the left, the limit from the right, and the value of the function there. Those things can actually all be different. Here, it happens to be the case that the limit as x approaches 2 from the right is equal to g of 2. They're both equal to 1. But the limit as x approaches 2 from the left is 3, which is different from those two. So the limit does not exist, but g of 2 is still defined. If this was an open hole here, and this was also open, then g of 2 would not be defined, even though both of these limits would still be 3 and 1 respectively.
And that would be marked as undefined, not does not exist, right? If they were both holes.
It depends on what is being asked for. So the limit would still not exist because the left and right limits are different, but the function value would be undefined. So if I asked you, what is g of 2? And both of these were open, you would say g of 2 is undefined or does not exist. That would be okay also. But the does not exist language is most often associated with limits. So we'll look at some more examples, and I'll try to give you every permutation of the way things can go wrong. But before we do that, let's finish this. The other spot of interest here is 5. What's the limit as x approaches 5 from the left?
2.
If I'm walking along the graph, getting closer and closer and closer to this point, what is my y value getting closer and closer to?
2.
Yeah, because I'm stuck to this graph. So even though the filled in point is down here, I'm stuck to this graph. So as I get closer and closer and closer to x equals 5, my y value is approaching 2. And if I were to approach 5 from the right, the same thing would happen. Still stuck to this graph, so as I get closer and closer and closer and closer, my y values are definitely still approaching 2. Therefore, the limit as x approaches 5 of g of x, does it exist or no?
Yes, it exists.
It does, and it's equal to 2, because that's the shared value of the right and left limits. However, what is g of 5?
undefined?
1.
It's 1, right? Because you've got this filled in dot down here at height 1.
Oh.
So here the limit does exist. The left and right limits do match each other, but the value of the function doesn't match that shared value of the limits. Let's turn to the homework problem that was asked about there, number 7. And then I've got 1 or 2 other little things like this I would like to show you. Yeah, this is good stuff. Try to make this a little bigger. And there's the x-axis, okay. So that's up there, 1, 2, 3. So we've got something like this going on that's filled in, and he's arcing off and doing whatever the hell he wants. And this is open. And then he's gonna snake over here. We've got 3, and then by 4, he's all the way up there. To here, which is also going to be open. And then from there, we just go off to the side. Okay. And we'll call this f of x. So this is the graph y equals f of x. And I'd like to investigate the behavior of the function near 2 and 4. I didn't miss anything there, right? Yeah, no. Okay, good stuff. So the limit as x approaches 2 from the left of f of x, what is that? If I'm walking along this graph, approaching 2 from the left, okay, that means I'm coming in like this. Again, each tick mark here is 1. So this is 1, 2, 3, and 4. So what is the left limit at 2? As I sneak in towards this point from the left, my y values are getting closer and closer to what?
3.
Mm-hmm. And if I look at the limit as x approaches 2 from the right?
3.
Well, that would mean I'm coming in from this way, right? So I'm stuck to the graph and I'm coming down and I'm coming closer and closer to x equals 2. My y values, they're getting closer and closer and closer to
1.
1, yeah. So the overall limit here, the limit as x approaches 2 of f of x without any directional indicators, no little plus or little minus, this does not exist. While we're here talking about 2, what is f of 2?
3.
Yeah, it's this filled in value up here. It's 3, because the point on the graph is this guy. This is a hole. Okay, let's look at what happens near 4. So if I approach 4 from the left, that means I'm coming along like this. What are my y values getting closer and closer to?
4.
Good. And if I came in from the right, so the limit as x approaches 4 plus of f of x, what is that?
Would that be 1 also? Or 4?
So 4 also, yeah. So we're getting closer and closer and closer from the right. My y values are going to the same place as they were from the left. They're coming up here towards this hole, which is 4. So what is true of the overall limit here? The limit as x approaches 4 of f of x, does it exist or no?
Yes.
It does, because the left and right limits are equal. And what is the value of that limit?
4.
4. Okay. Also, what is true here? What is f of 4?
Undefined.
Good. Yeah, this is undefined. Why is f of 4 undefined?
So there's a
Not
hole in
given
the graph.
point on the map, on the graph.
So you're both right. I want to contrast what's going on here to what's going on here. There was a hole here, but we didn't say f of 2 is undefined. We said f of 2 is equal to 3. What made f of 2 3 is the fact that when you look for a point associated with x equals 2, if you look for a point along the vertical line x equals 2, there is a point. It's this one, and its y value is 3. If we look above x equals 4, there is no point. There's just the hole. So there is no y value associated with x equals 4. There is no output on this graph when you plug in x equals 4. So f of 4 here would be undefined, even though the limit exists. So this is the thing that's usually tricky for folks at the start, is divorcing in your head the concept of the value of the limit, the value of the function. And it can get a little bit worse. Let me modify this just a teensy bit. Everything we said about 2 in the previous example is true here as well. Right? If this y value here is 3, this y value up here is 4. But here, the limit as x approaches 4 from the left and from the right would still exist and still have that value 4. But f of 4 would be this value up here, maybe 5. So the value of the limit would be this y value, but the output from the function f of 4 would be this. So here, the limit as x approaches 4 of f of x would still be 4, but f of 4 itself would be 5. So what we're seeing are different types of discontinuities. Something like this, where the height takes a drastic jump, is called a jump discontinuity. Something like this, where if I just drag this point and put it in the hole, the discontinuity would go away, is called a removable discontinuity. And we'll talk a little bit more about types of discontinuities when we get to section 2.5. But I wanted to see, just check or elaborate a little bit on the difference of the situation here, where you've got a hole and then nothing above or below to fill it in. The function value there will be undefined, even though the limit exists. And it's also possible that the limit exists, but the function is defined in a way so that the value of the function doesn't match the value of the limit. So the limit doesn't care about what happens at 4. The limit cares about what happens very nearby 4. And that's the core concept of a limit and the connection to open intervals. I'm not interested in what happens right at this point. I'm interested in what happens really, really nearby. And I'd like to make some sort of statement about getting closer, as close as you want. The word is arbitrarily close. So if x is arbitrarily close to 4, then f of x will be arbitrarily close to whatever the value is, in this case, also 4. You feel kind of comfy with this idea? Okay. So let me grab something a little more challenging. What do we have here? Oh yeah, we still need to talk about infinite limits. Where's your homework? I wanted to do one more tricky-ish problem from your homework. And then we'll talk about infinite limits. Yeah, that's fun. That's more of the same. Okay, let's do something like that. So everybody here has taken trigonometry, but I would be surprised if everybody here had seen this function. Pretty crazy looking, right? What's going on there?
Can't see anything.
Can't see anything.
No? Okay, hold on. Let's see, it should be sharing the whole screen. What about now?
There we
Yeah,
go.
can see it.
Okay, so this is the sine of 1 over x. And what's happening is that as x gets closer and closer to 0, this 1 over x is getting really big, which makes the sine function wobble back and forth faster and faster and faster. I might be able to, yeah, kind of zoom in a little bit on that piece for you. You see these oscillations getting faster and faster and faster and faster and faster as you get closer and closer towards 0 here. So it gets really hard to say what the hell is going on near the origin. This graph gets so dense. This is another way that a limit can fail to exist. And you do have an example like that in your homework. So I'm going to sketch something over here. We'll just say discuss the limit as x approaches 0 of the sine of 1 over x. And I'll give us the graph. It's still a sine wave, so it's still bounded between 1 and -1. But what's happening is out here, maybe the oscillations are pretty reasonable, but as you get in, they start to pile up. Something absurd like this. So again, my art is bad and I feel bad. You can do your best to mimic this picture. I'd like to be able to say as x gets closer and closer to 0, does y get closer and closer to some value? Right, this is the question we want to answer. And again, I'm sorry for this terrible art. I'll do my best to correct it a little bit. So like this. The answer is no, because suppose you could pick some value in here, some y value that you would want to call that limit, maybe 0 or maybe 1. If you zoom in, no matter how far you zoom in, whoo, let's get off. No matter how far you zoom in, the thing will be oscillating back and forth infinitely many times between where you are and 0. So there's no like sneaking up on any particular value. So when you see these oscillations getting out of control here, this is also a case where you would say the limit does not exist. So because the function's y values oscillate so rapidly between -1 and +1 near 0, there is no y value that we approach as x goes to 0. From the left or from the right, it doesn't matter.
What would happen if you plug something in, like f of x equals 1? Like, what would you get? Or 0?
If you tried to plug x equals 0 in here,
Yeah.
it would be undefined. You'd have the sign of 1 over 0, and 1 over 0 is not a number. It does not exist. So you'd be asking the sine function to return an output for an input that does not exist. Desmos is usually pretty good about letting you click around and actually locate the hole, and it'll say undefined, but because this graph is so dense, we can't actually do it here. There are ways to sort of try to control for that, but I don't want to spend too much time here. Definitely it's true that sine, come back here, sine of 1 over 0 is undefined because 1 over 0 is undefined.
What if you had like sine of 1 over 0.0001?
That's what we're trying to get at. So let me pull up, I think I still have this tool here, the coronavirus section.
Yeah, I just want to say, so as you'd get closer to 0, it would just oscillate up and down between 1 and -1. And so it would just keep oscillating, so you can't really define a limit.
Exactly, yeah. Let's see, I think.
Like infinitely. As you get closer to 0, it goes faster and faster and faster and faster and faster.
Precisely. So let me find for you a TI-84 emulator, and we can look at a table.
I mean, if you do 1 over 0, I mean, personally, I think think of that as infinity. Like, and what sign of infinity? You don't really know.
There are some ways to think about 1 over 0 as infinity legitimately. But yeah, the sign of infinity.
Yeah, but then again,
is not
if we
defined.
approach it from the right side, it's positive infinity. If we approach it from the left side, that's negative. So yeah,
We'll get
don't
to
really,
that.
yeah.
Yeah.
But there's not really a way.
This is bogus. So if you were to make a table of values, if you were to try and compute like x equals 0.1, x equals 0.01, x equals 0.001, x equals 0.0001, this would be a reasonable way to try and guess at this limit. But what you're going to notice is that there's no nice connection between those outputs. There's no nice pattern. I'll come back to the calculator portion of Desmos. And we can ask for these values. So the sine of 1 over 0.1, that's 0.17. The sine of 0.01, that's 0.9. Sine of 0.001 is negative 0.9. The sine of 0.0001 is negative 0.9 again.
So technically it's not undefined. They have definitive answers.
Well, no, so there are
I think it just glitched right there.
It did, didn't it? Yeah, I think.
Can't compute it. Yeah, I just can't compute it, I guess. Does that?
Oh, yeah, it's a rounding error. Yeah. So
okay.
see,
Yeah.
definitely if you plug in 0, it's undefined. And if you try to sneak up on 0, what you won't find is a nice pattern. We're running into rounding errors there. But if you build this table, what you'll notice is that these y values, these don't follow any nice pattern. They don't get closer and closer to any particular number. Because maybe the 0.01 is somewhere here towards the top, and you come in just a little bit and you land somewhere near the middle. You come in a little bit and you land further down the bottom. You come in a little bit, maybe you're towards the middle. It's bouncing back and forth so rapidly near 0 that as you try to walk in, your little guy is going up and down that hill infinitely many times, really, really fast. So his y values are not stabilizing. They're not getting closer and closer to anything. So the limit there does not exist. Even the left and right limits individually do not exist. And that's not something we see a lot in this class. Usually for us, either the left or the right limit will exist, and we can try to discuss about whether or not they're equal. But with this sort of rapid oscillation, you'll be walking up and down that sine wave very, very quickly as you come in. So there's no reason to expect a nice pattern here. So if we wanted to see, Where did that go? One of your homework problems has something similar to this. Here, right? So here you have this kind of dense, rapid oscillation getting faster and faster as you approach 5. As you approach 5 from the right, it looks like you are getting closer and closer to 3. But as you approach 5 from the left, look, we're going up, down, up, down, up, down, up, down, up, down, up, down. So fast back and forth that my y values, it's hard to say, am I getting close to 4? Am I getting close to 2? Am I getting close to the thing in the middle? None of those necessarily. I'm bouncing back and forth between 2 and 4 infinitely often between here and here. So the limit as x approaches 5 from the left here would not exist, even though the limit as x approaches 5 from the right does. Okay. So if you have the graph of the function, calculating limits is not all that bad. Another fun thing to do is to give yourself a set of criterion and see if you can draw a function that has those properties. So you could say, sketch the graph, or sketch the graph of a function, call it f of x, satisfying the following. We can ask that the limit as x approaches 0 from the left of f of x be -1. The limit as x approaches 0 from the right of f of x is +1. We could ask that f of 0 itself be like 3. And let's put in some conditions at another value. Let's say also that we'd like the limit as x approaches 2 from the right to be, how about 4? And the limit as x approaches 2 from the left to also be, f of x, sorry, also be 4. And then we'll have f of 2 maybe being 0. So we've got these 6 criterion here. Could we come up with a function that has these properties? We don't have to find an algebraic expression for it, but could we draw a picture? Could we draw a graph that has these properties?
Yes.
Yeah, I mean, sure, I hope so. But it's going to require just a little bit of thinking. Okay. So I know I want f of 0 to be 3. So the point 0, 3 should be on my graph. And I know I want f of 2 to be 0. So the point 2, 0 should be on my graph. We can start there. I know I want the limit as x approaches 0 from the left of f of x to be -1. So over here, as I get closer and closer to 0, my y values should be getting closer and closer to -1. So that means I'm going to have something like this going on over here. It could do whatever sort of weird wiggly stuff you wanted, but it's got to have something like that going on over there. And I want, as the x approaches 0 from the right of f of x, the limit to be +1. So that means I've got to be doing something over here like this. As x approaches 2 from the left, I want to be getting up to 4. So that means I have to get up to here. And as x approaches 2 from the right, I want to be getting close to 4. So something like this would work. And it could be piecewise linear. These could be whatever sort of curves you want. The idea is that as you approach 0 from the left, you go towards -1. As you approach 0 from the right, you go towards +1. As you approach 2 from the left or from the right, you're going towards +4. So conjuring things like this is a worthwhile exercise to go over. WebAssign has a few problems like that, but one of WebAssign's great flaws, maybe its greatest flaw, is that I can't make you draw all the things by hand, right? It has you pick from a few, or maybe, you know, it'll have a little graphing utility and you can graph something, but it doesn't allow the sort of freedom that drawing graphs by hand allows. So I want to strongly encourage you guys, as you solve problems, draw these pictures, right? Draw them for yourself. It's not the same to pick from the set of 5 pictures that WebAssign gives you or whatever to draw it yourself.
I had a question.
Yeah, go ahead.
So I don't know if this is, it's just kind of like a side thing.
Mhm.
So does it really not matter when graphing these to get like the proper end behavior?
Not for this, because none of the restrictions they gave us had anything to do with end behavior. But we
So it really doesn't matter how it's graphed, like in that aspect then.
yeah, really, this could be piecewise linear. You know, it could be constant over here, linear here, constant here, and that would work also. So because they didn't give us anything demanding a particular end behavior, you could pick whatever end behavior you wanted here. That would be fine. Other questions on this one?
I had a question, but it wasn't about this. It was about a homework problem.
We can take a look. Sure, there's one other thing I want to talk about today, but we can take a look at one more homework problem.
Yeah, it was 3B.
We're getting close. All right, 13 you said?
3B.
3B. Ah, yeah. So here you're calculating slopes of secant lines, right? You're calculating average speeds, average rates of change, over ever smaller intervals to try and approximate the exact speed when t is equal to 1. So you would calculate each of these slopes, and then you'd ask, is this getting closer and closer to something? So I have to let you guys go in just a few minutes. I can put off the infinite limit stuff until Friday, and we can take a closer look at this. I think that's okay. So let me write this guy down. The height after 2 seconds is y equals 56 t minus 1.86 t squared. And we want to find the average speed over 1 comma 2, 1 comma 1.5, 1 comma 1.1, 1 comma 1.01, and 1 comma 1.001. All right. So this is that idea of bringing secant lines closer and closer to tangent lines. The graph of this function looks something like this. It's a parabola opening down. Maybe here's 1. And they have you calculate a whole bunch of slopes of secant lines. So you start with this guy from 1 to 2. And then they have you do 1 to 1.5. And then 1 to 1.1. And the goal is to get closer and closer to figuring out the slope of the tangent line here. So you're dragging these points closer and closer to this base point to try and get a feel for the slope of the tangent. So this would be, we'll call this thing f of t or h of t. This would be h of 2 minus h of 1 over 2 minus 1. This guy would be h of 1.5 minus h of 1 over 1.5 minus 1. This would be h of 1.1 minus h of 1 over 1.1 minus 1. This would be h of 1.01 minus h of 1 over 1.01 minus 1. And this last guy here would be equal to h of 1.001 minus h of 1 over 1.001 minus 1. I'm limited in time here. As you compute these numbers by plugging into these formulae, you'll notice that these outputs, the numbers you get, will be getting closer and closer to some fixed value. Your goal is to guess at that fixed value. So here, if I wanted to figure out this first guy, h of 2, well, that's 56 times 2 minus 1.86 times 2 squared. And then from that, you would subtract 56 times 1 minus 1.86 times 1 squared, and divide all of that by 2 minus 1, which is 1. You would do the same thing for each of these. And then hopefully you'll notice a pattern in these outputs. They'll be getting closer and closer to some particular number. Part B, they want you to just guess at what that number is. Now I think our class is 12:30 to 1:45, right? So I think we might not have time to go through this. Let me see when my next class is. If you want to hang around, I might be able to sit here and grind on this for a minute. My next class starts right at 2, so I'm afraid I do not have time. But that's the thing. So compute all these slopes, and then ask yourself, are these getting closer and closer to some number? The answer to that will be yes. And the number that those slopes are getting closer and closer to, that's your answer for part B.
I mean, I was thinking you could do Desmos. You could just like do f of like a minus f of b all over a minus b, and then just drag them closer.
That's true. Desmos is pretty good at these sort of things. So if I tell it f of x is 56x minus 1.886 x squared, then I think I can ask for things like f of 2. Yeah, minus f of 1. So that would be your first guy. Your next guy would be f of 1.5 minus f of 1 over...
Oh, I think you're forgetting to divide. Okay, 1.
So the first one, the thing downstairs is 1. It's 2 minus 1, right? But it's the same. And yeah, you could...
Oh, right.
You could continue doing this. F of 1.1 minus f of 1. Parentheses divide by 1.1 minus 1. F of 1.01 minus f of 1 over 1.01 minus 1. F of 1.001. This is our last guy, minus f of 1 divided by 1.001 minus 1. So these numbers do appear to be getting closer and closer to something, right? 50.42, 51.35, 52.094, 52.26, 52.27. We could take it further. And further still, if we're not sure. And you see these numbers starting to stabilize, 52.2, 52.2, 52.2, 52.2. The second figure has stabilized here, 52.27, 27, 27. And what we're really doing here is we're approximating a limit. So as we let this number get closer and closer to this number, that's the same thing we're doing along those graphs by trying to ask, as our x value gets closer and closer to a certain number, what is the output getting closer and closer to? The difference here is that you're working within what's called a difference quotient. So you're taking a limit of something that we haven't really talked much about, and that's why we have you experimenting numerically. But I would say this is getting closer to 52.28, right? That appears to be the case. these 9s, if these trailed on forever, that would be 52.8. So the computation there is kind of boring. It's not a lot of fun, but the goal is to get you noticing this pattern. And if possible, to make a connection to something like this. So each of those numbers we just computed is one of the slopes of a red line like this. And as you bring those 2 points closer and closer together, you get closer and closer to what's called a tangent line. And the slope of that tangent line is the thing that we're really after. So we'll talk more about this stuff on Friday. We're going to talk about infinite limits. And then next week, we'll start playing around with these difference quotients and getting to a place where you can connect the two ideas, the idea of the limit and the idea of the secant and tangent lines. All right. So this is where we're going to have to end for the day. Practice calculating these limits from the graphs. This is the main skill that we're worried about right now. And we want to make sure that you're comfortable with the difference between the value of the function and the limit of the function at that same point. And once we have that pretty solid, we'll be able to return to this concept of tangent lines and have the tools to actually do the calculation instead of all of this horrific numerical stuff. Alrighty. That is where I'm going to end the meeting for today. If you guys want to talk a little bit more, I invite you to come by my office hour this afternoon. Otherwise, I will see you on Friday.